In 1974, we sent a message into space. 1,679 ones and zeros fired at a cluster of 300,000 stars. And hidden in that tiny string of digits is a picture. A picture that says what we're made of, what we look like, where we live, and how we sent the message. The trick is knowing how to decode it, and so that's what we're going to do. This thing, the Arecibo Message, is honestly one of the coolest things I've ever heard of in my entire life. It's November 1974, and the Arecibo radio telescope in Puerto Rico, this gorgeous, slightly Bond villain 305-metre dish set into a limestone sinkhole, has just had a major refit. New aluminium panels, a new radio receiver, the whole works, and someone at Cornell has an idea for the reopening ceremony, which, depending on your point of view, is either profoundly pointless or deeply moving. Sending a message to the stars. Now, this wasn't some whimsical wouldn't this be fun after one too many pints at the staff Christmas party. This message was devised by Frank Drake. Yes, that Drake of the Drake equation, with help from Carl Sagan and others. The thinking was quite straightforward. We've got the most powerful radio transmitter on the planet. Why not use the reopening ceremony to send a kind of cosmic calling card up into space? A message for aliens, a message that says in the most compact way possible, we exist, and here's a little bit about us. The target was M13, a globular cluster of stars about 25,000 light years away in the constellation of Hercules. Just to manage expectations here, that means the message won't arrive for another 25,000 years, and should anybody receive it and send one back, it means it's a 50,000 year round trip, so if you're waiting by the phone, you might want to have a really long book with you. In truth, the Arecibo Message was never really about making contact. The chance that anybody will receive it on the other end is minuscule. It was more a message to ourselves than anything else. Us saying we can talk across the cosmos should we choose to. So, how do you actually shout across space? Arecibo transmitted at 2,380 megahertz. That's in the microwave part of the spectrum, chosen because it can cut through Earth's atmosphere easily before it speeds off into space. The message itself was 1,679 binary digits long. Ones and zeros transmitted at very slightly different frequencies, just 10 hertz apart. Each bit lasted 100 milliseconds, so the entire message took 169 seconds to transmit. And that's it. The entirety of humanity's first deliberate interstellar radio message was shorter than the average pop song. We are, if nothing else, concise. The number 1,679 is itself a clue how to decode the message, because it's a semi-prime, the product of two prime numbers, in this case 23 and 73. The beautiful thing about a semi-prime is that there are only two ways you can arrange the number 1,679 into a rectangular grid. It's either 23 by 73 or 73 by 23. That's it. They're your only two options. The message itself therefore tells you its own dimensions, at least assuming you know enough to factorise a semi-prime, which, let's be honest, is a pretty low bar for a civilization capable of receiving interstellar radio messages. If you can build a radio telescope but you can't factorise this number, something has gone horribly wrong in your education system. If we try 73 columns by 23 rows, you get gibberish. It's just noise. There's no pattern at all. But if you arrange them as 23 columns by 73 rows, the hint of a picture appears. Even when it's rendered like this, you can sort of make out the shadow of an image. It becomes even clearer when you squint at it. You can imagine an alien life form going to the maid. Is it just me, or does it look like there's something there? And it becomes even clearer when you colour the zeros and the ones differently. To save you the trouble of having to squint for the remainder of this video, or be completely bamboozled by all those ones and zeros, which, to be honest, make my eyes go a bit funny, I'll render this as a grid of binary squares. 1 means on, 0 means off. And that right there is the first act of decoding. So now we've got this little patch of pixel art. It looks a bit like something from a vintage Game Boy or a really ambitious cross-stitch project. It's blocky, it's crude, but it's honestly one of the most elegant things human beings have ever made. Packed into this tiny grid is our counting system, our chemistry, our biology, our home, and the machine that we use to send the message. Each of these sections really is a small miracle in information density. Drake and his team had to send all of it in less than 1,700 bits of information. They had to be absolutely ruthless about what to include and absolutely ingenious about how to encode it. So we start at the top of the grid. At first glance, it's not obvious what it means. There's a repeating structure, columns and dots getting gradually more complex. Something is clearly building, but what? Well, if you know anything about maths, and given that you've just received an interstellar radio transmission, we're going to assume that you do know something about maths. This might look familiar. The first column has 2 filled squares. The next has 2 as well, but in different positions. The third has 3, and so on, each column getting a little more complex. It's a counting system. They're numbers written in binary. And it makes sense to start here because maths isn't some arbitrary human invention. It's the fundamental language of the universe. 2 plus 2 equals 4, whether you're in Puerto Rico or M13. Aliens might not have eyes, they might not have DNA, but they will have maths. So let's have a look at how these binary numbers work, because it's actually simpler than most people think. Take a column of squares, reading bottom to top. The bottom square is worth 1. The next is worth 2. The next is worth 4, and then 8, then 16, and so on. Each square is worth double the one under it. And every square is either on or off, filled in or empty, 1 or 0. To read a binary number, you just add up the ones that are switched on. 1, 2, 3, 4. You see the pattern. With these simple powers of 2, you can build any number you like whatsoever just by picking the right combination of squares. And that's exactly what the Arecibo message does. Each number from 1 to 10 gets its own column. The very bottom row of each column is just a marker that says a number starts here. Now, here is a really nice detail. The numbers 1 through 7 fit comfortably on a single column because 3 binary digits can represent everything up to 7. But the number 8 needs a 4th digit, so the numbers 8, 9, and 10 spill over into a second column. The message handles this really gracefully, and it's a valuable lesson rather than a quirk. It tells the recipient that if a number is big enough, it can just overflow onto a different column, and this becomes really important further down the message when we start to decode massive numbers. Okay, so that's the counting system. What's next? Immediately below the numbers, we get 5 more numbers. And if we decode them one by one, we get 1, 6, 7, 8, and 15. Do these numbers ring a bell for anybody? Well, they might if you're a biochemist, because these are the atomic numbers of the elements of life. Hydrogen, carbon, nitrogen, oxygen, and phosphorus. The 5 elements that make DNA. Now it gets properly ambitious and a lot more bio-heavy because this section encodes the molecular biology of DNA, which sounds like an impossibly huge amount of information to pack into just a couple of rows of pixels. Each molecule is encoded as a group of 5 numbers, one under each of our 5 elements from the section above, telling you how many atoms of that element are in the molecule. Let's decode one in full so you can see what I'm getting at. Let's take this one, which is actually repeated here, here, and here. Reading across the 5 columns, we get 5 binary numbers, 1 under each element. 7 under hydrogen, 5 under carbon, no nitrogen because the column is empty, 1 oxygen, and no phosphorus either because that column is empty too. If you've done any biochemistry whatsoever, this will look really, really familiar. It's the sugar backbone in DNA. It's the deoxyribo in deoxyribonucleic acid. Now, this one, O4P, the phosphate group, completes the backbone of our double helix. And now we've got as backbone, we can decode the 4 molecules in the middle. This one gives you 45500, H4C5N5, which biochemists will recognise as adenine. This one gives you 55220, H5C5N2O2, thymine. This one gives you 44310, H4C4N3O, cytosine. And finally, this one gives you 45510, H4C5N5O, guanine. These are the 4 bases that make up the rungs of the DNA double helix. I think this is so smart, it's just brilliant. I think it's my favourite bit of the whole message. It's saying, look, this is some chemistry and it's really, really important of us. It's fundamentally a molecular self-portrait of life here on the Earth, which is about the most fundamental thing you can say about us and all of the living things that we share the planet with. Straight underneath the chemical representation of DNA are two twisting lines winding around a central axis. This is the form of DNA, a graphical representation of the double helix. Down the middle of the double helix, in the place where the base pairs form the rungs, we've got a number, and you can tell just by looking at it that it's really, really big, but we can decode it using exactly the same rules that we used earlier. Doubling the value in the binary column each time, and then adding together the values that are switched on, we get approximately 4.3 billion. It's running right down the middle of the double helix, just as the base pairs did above, indicating that this is the number of base pairs in the human genome. Note that this is a slight inaccuracy. 4.3 billion was the best estimate in 1974. The year the message was transmitted. We know today that it's actually closer to 3.2 billion, so we were a touch high, but it wasn't that bad considering we wouldn't actually sequence the entire human genome for another 30 years. Either way, it doesn't really matter. This part of the message would make the same point. Our genome is long, and we are complicated organisms. Now, this is maybe the most charming bit of the message. There's a little stick figure, arms outstretched, feet apart, looking for all the world like it's about to do a star jump. It's adorable, but it's also doing some serious work. First of all, the DNA double helix winds its way down and finishes very close to, and actually overlaps slightly with, the head of this being, indicating that there's a very tight relationship between the molecular biology and the being itself, which, of course, there is. Then there are the two things either side. The one to the right is another number, but this time rotated through 90 degrees. It's just about possible to tell this because of that handy marker square. If we rotate it, we can decode it using exactly the same system as before. Working our way up the columns, doubling the number each time, and then adding up all the squares that are switched on, gives us 4.3 billion. It's not super obvious what this number means, but if they were to figure it out, then they'd get the human population at the time the message was sent. I do wonder if they would imagine a planet with 4.3 billion of these things clanking around on the surface. Now, the thing on the left is the height of a human. The vertical bar, which runs from head to toe, indicates it's a scale bar, and the thing running horizontally is the length of the scale bar. If we decode the number, we get 14. But 14 what? As your high school science teacher constantly and correctly reminds you, a number without a unit is largely meaningless. So, what unit do we use? Extraterrestrial intelligence would not know what a foot or a meter is because they're arbitrary units, they're arbitrary human inventions that we made up for our own convenience. Lucky for them, we did smuggle the unit into the message itself, the wavelength of the radio waves we transmitted. The extraterrestrials would have to know this length to possess the message at all. Multiplying our binary number by the wavelength, 14 times 12.6 centimetres, gives us 176 centimetres, or about 5'9", the height of your average human. Below the human figure is a row of blocks representing our solar system. The sun on the left, the biggest, and then 9 planets. Yes, 9 planets, because this was 1974, when Pluto was still in the club. Poor Pluto, demoted in 2006, but at least forever immortalised in our first interstellar message. I think there's a kind of poetic justice in that somewhere. You'll notice that Earth, the third block from the sun, is shifted up slightly towards the human figure. That indicates that we live here. It's simple but effective. The relative sizes of the blocks gives a rough sense of the planet sizes as well. And finally, the bottom of the message is a sketch of a radio telescope. Below that is a number encoding the diameter of the dish itself, recognisable because of that handy starting square on the number. If we decode the number, we get 2,430. But remember, it's in the units of the transmission wavelength, which gives roughly 306 metres, which is within far less than 1% of the actual diameter of the Arecibo dish, 305 metres. That is not bad for a 23 pixel image. And by telling the recipient the physical scale of the instrument that we use to send the message, we give them a sense of how mature our technology and therefore our civilization is. And here's the thing, this would actually be recognisable to extraterrestrials. To receive the message in the first place, they would have to have invented something like a radio telescope. It wouldn't be some alien artifact, it would look familiar. This is our way of saying, we've got one of these too. And so there we have it. In 1,679 bits, Frank Drake and his colleagues encoded quite a lot about us. It's an absolutely fantastic piece of design. And yes, I know, no one is ever going to receive the Arecibo message. M13 will have moved a bit by the time it arrives and will miss, and the radio transmission will have spread out and thinned as it traverses the 25,000 light years. And even if it did arrive laser focus, the chance that somebody or something was in exactly the right place with exactly the right instrument, pointing at exactly the right patch of sky at exactly the right time are, well, we can call them modest at best. But that was never really the point of the Arecibo message. It's less a letter and more a thought experiment made real. If you had 1,679 bits with which to communicate something about humanity, what would you say? And how would you say it? The Arecibo telescope is in ruins today. It collapsed in 2020. The cables failed and the 900-ton instrument platform crashed into the dish. But the message is still out there, travelling at the speed of light, currently about 52 light years from Earth, washing over star system after star system. Whether or not anyone decodes it, I think the Arecibo message says something wonderful about humanity. We looked up to the sky at 300,000 stars, 25,000 light years away, and thought, they should know something about the Earth and its inhabitants. And I absolutely love that. If you enjoyed watching this video as much as I enjoyed researching, writing and recording it, I'm obliged to remind you that you might want to subscribe. This is still quite a new thing for me, and so let's see how it goes. Bye for now.